Hi, everyone. And thanks, Manuel, and thanks, Paolo, for inviting us. My name is Marco Paini, and I work for Rigetti in the UK. I'm currently leading the program that Emanuele just mentioned, which I will talk about in a little bit. Leave it to Alex for his introduction, then I'll share my screen and start sharing some slides.
Hello, everyone. I'm Alexey Kondratyev, Head of Data Science and Innovation at Standard Chartered Bank. Together with Rigetti, we participate in a consortium building the first commercially available quantum computer in the UK. And today, I will be talking about one particular use case, which I believe is very interesting and brings us one step closer to demonstrating quantum advantage. Marco, over to you.
Thank you. Okay, so let me do the screen share. And please tell me if you... Okay, yeah.
Oh, we see the entire PowerPoint application, but yeah, perfect.
Okay, perfect. Okay. So two main things we'll cover, and I think we'll leave quite a bit of space for questions. So we'll talk a little bit about first the project overall, and I will do that, and then as Alexey had alluded to, one specific use case. Now, first things first, quickly. So Rigetti is a full stack quantum computing company. We build all the components from the quantum processors to the software to the development framework that allows programming of quantum computers, and we make the services, so the access and then the ability to program quantum computers available on the cloud. So we cover fundamentally the full stack. The company is based for the most part in California, in Berkeley and Fremont, and we have offices in the UK and in Australia. Okay, a little just quickly the context of the project. So as part of the Industrial Strategy Challenge Fund, one of the 23 challenges that were created as part of ISCF is a quantum challenge that has gone through, the program has started now, has been around for some years, and it's gone through different waves. We are at present in wave 3, and actually I believe last week there was even a quantum meetup on the latest sub-wave of wave 3. So we participated at the end of 2019 as a consortium including Rigetti, UK, Standard Chartered, but also Oxford Instruments and Phasecraft, which is a UK startup that does quantum simulation software, and the University of Edinburgh. We participated in the competition with a project, which is the one that I will talk about, called Quantum Computing Platform for NISQ Era Commercial Application, where NISQ stands for Noisy Intermediate State Quantum, which is fundamentally how today's quantum computers are defined. So still at an intermediate scale and with some noise, with some errors. We were successful in the competition, and the project started in September of last year, 2020, and it is a 3-year project, so that will continue until August, at the end of August of 2023. Now, a little bit about the project. What is the project? And actually, I'll talk a little bit about also the reasons and how we've come to, defining the proposition. So the first, I think, the original observation that actually led to define the project really started from just a simple observation, which was that the UK quantum ecosystem is particularly active, both at the startup level and at the academic level. But there was one evident gap, which was actually the availability of a physical quantum computer of some size. where some size means, the tens of qubits. So the core of our proposition, and it still remains the core of our proposition, was building a quantum computer in the UK, and do that at with speed, and that is leveraging the technology that had been developed by Rigetti in the US over the years. So building a quantum computer is difficult, and is particularly difficult if starting from scratch. So our idea was to try to stand up a quantum computer within a year or so from the start of the project, and again, of a size that is comparable to the largest quantum computers around. Now, we soon realized, actually, let me actually just show a couple of pictures. Unfortunately, we don't have pictures. This is more of a curiosity. I don't have pictures, or I should say, I do have pictures, but they're not good enough yet of what we're building at the moment. So I'll be happy to share the real pictures in a few months. So this is just a view of, say, what quantum computers in a small quantum computing data centers look like. This is for the ones that might just be curious about, wondering what a small quantum computer data center looks like. So quantum computers are contained in those cylinders, and the stuff that is connected to it is all the classical systems that control them. Now, again, as a curiosity for the ones who haven't really seen the inside and wonder what it looks like. So this is what's in those cylinders. And actually, the true quantum computer is just that tiny little disk here at the bottom. That is, and maybe I should even say, the core of that is something that is under the center of the disk here. And that is truly the QPU, the quantum processing unit. So this is an old QPU that was fabricated by Rigetti. And again, we fabricate pretty much, so the QPU, and we assemble all of the components. So all of these things that you see here that make it look very complicated, they are all fundamentally control systems. Now, not all quantum computers look like this, by the way. Just as a note, this is what Rigetti, IBM's, and Google's, for example, for the most part, they look very similar, and this is what they look like. Now, there are others that, on different technologies that look quite different. Now, again, we have at Oxford Instruments, where the quantum computer is being built now, we have a fridge that is undergoing final test that looks very much like the picture that I've shown you from Berkeley. But the rest isn't ready yet, so I'll be happy to share proper pictures as soon as they're ready. Now, when we thought of this idea of deploying a quantum computer, we soon realized that just deploying hardware wasn't sufficient to trying to create commercial value. And as we were thinking through this, I think obviously the first thing that comes to mind is that is also necessary is applications. And it's almost, by definition, it's almost obvious given that there's nothing you do without applications. And even that isn't sufficient, because you need then the consumers of those applications. So you need end users. And so we refined the original definition of the scope by thinking, by including these elements and actually thinking about which applications and what sort of engagements we wanted to try to build. And when it comes to applications, I think there are two types, both important. One is at the level of error mitigation and quantum verification. So all of those things that actually support the present quantum computers that have still need quite a bit of support. And again, that is because of the presence of noise and errors. And even because of our inability in principle to even be able to say whether a quantum computer that is large enough has made correct computation or not. And that's, so that's quantum verification. And then there's the other set of applications, which are actually the applications that are for the use of end users. And so in particular, industry applications, and the spectrum goes all the way from financial services to energy and pharmas, etc. So we wanted to build a program that integrated all things, and not only because they're all important aspects, but also because there's some sort of there are benefits. So the work on each feed in to the other work stream. So in other terms, by working with real hardware and having application teams testing on real hardware, you actually realize and feedback requirements. You realize what things work and what things don't work as well, and you feed requirements back into hardware teams, and then vice versa. By doing work on applications and specific class of algorithms, you realize which things are actually possibly more useful for specific industry applications. As again, in some cases, that isn't necessarily intuitive. So the final, I suppose, the final thing that we wanted to put together was, if this was the vision, was making sure that actually first we picked the right set of applications, but also we had the right team to be able to deliver on that vision. And so, and I haven't said it clearly, sorry, Rigetti is the lead in this consortium, and we started originally in defining, making this exercise around defining what was possible interesting scope. And so Oxford Instruments has been leader globally in cryogenics for some time. They had an interest in growing in quantum computing specifically. And so that, when it came to the dilution fridges, which are needed by quantum computers, we decided to partner with Oxford Instruments. We hadn't done it in the past. So in Berkeley, we're not been using to date Oxford Instruments technology. So that is a different setup from what we have in California. And not only that, I think we've, Oxford Instruments also, demonstrated interest in possibly looking at, offering a quantum computing as a service offering. And so Oxford Instruments not only is providing the dilution fridge, but they're also providing the hosting facility and hosting services. So right now the system is being built at Oxford Instruments premises. And then when we thought of applications, there are, I think, there are two areas that are right now considered as key applications for end users. One is simulation of physical systems, also known as quantum simulation, with so molecular chemistry or solid state simulation. Applications are for science, material science, for drug design, and etc. And Phasecraft is a small startup based in the UK, funded by academics, a professor from Bristol University and two professors from UCL. And they really represent excellence in the space. And so we've set up a quantum simulation work package with Phasecraft to explore quantum applications applied to simulation of physical systems. Now, the other area is again considered as one of the most promising near-term areas for quantum computer is quantum machine learning. And the University of Edinburgh had done some really interesting work around some aspects of quantum machine learning. And with Standard Chartered and with Alexei, we had already collaborated and had several conversations in the past on specifically in one area, which was generative models and the use of quantum computers for generative models. And so this is how we started shaping this idea of exploring quantum machine learning applications applied specifically to finance. Now, finally, as I was saying, there's another class of applications quite different, which is applications that are for the to support the early quantum technology or today's quantum technology. And so the University of Edinburgh has also been at the forefront of research in the so-called quantum verification. So quantum verification, again, consists in finding efficient protocols to verify the computations of a quantum computers. This is far from obvious, and the reason is because we want quantum computers, in fact, to do computations that cannot be done classically. That's the whole point. Now, that raises, of course, the question of how do we verify that that quantum computer did the result of the quantum computer produces correct or correct within some bound. And so that is the entire field of quantum verification, coming up with things that are efficient enough to be able to be done classically that give us an indication of the correctness of a result. I have to say, if quantum verification was the original scope of this work package with the University of Edinburgh, we have expanded this now, and we are actually dedicating more attention to another thing, which is error mitigation or quantum error mitigation, which is the study of protocols that instead mitigate the effects of noise and errors in today's processors. So both things are really important, and there is a great deal of research that is ongoing on error mitigation. And it is key, together with quantum verification, to be able to get to the point of first making a computation that is good on a quantum computer, and also, you know, we can certify that it is good and it is at a level that classically cannot be done. That's the whole point. We have also thought a little bit about the engagement with the broader community. For now, we are focusing really on laying the foundations of the program, so building really the hardware and the initial demonstrators of these quantum applications. We'll soon get to focus a bit more, in fact, on engaging with the broader ecosystem. And in terms, I suppose, of where we are today, and let me just move on to this slide. It's very similar, but it's got a summary of the deliverables. In terms of where we are today, I think the objectives are, so the facility in Oxford Instruments is almost completely built. And so is, well, the fridge is also completely built. It's going through final testing, and it's soon going to be, in fact, as early as possibly next week or maybe the one after, through acceptance test. We are producing and starting to work on various components that will be shipped from the US to the UK, and that is because the core, in particular the QPU, still needs to be fabricated in the US. We have hired the team in the UK, and in fact, they will all be starting in the next 2 months or so. And from, I would say, May, the activities in the UK will intensify. The physical build activities in the UK will intensify, and will try to get the system up and running towards the end of this year. This will be a first system. We're planning to upgrade towards the end of next year to a larger system, trying to keep up with, in fact, the roadmap that we have set overall as a company. So we are still targeting to have, by the end of next year, a system with more than 100 qubits live in the UK. That is still the key deliverable, having a 100+ qubit system live in the UK. And together with that, we've got, you know, a few more that can really be summarized in 5 things in total. And they're all, you know, relatively ambitious, depending on how far we'll be able to manage to push these and results, in particular when it comes to results of quantum machine learning and in quantum simulation, and in quantum verification and error mitigation techniques. As an example of some of the stuff that we are doing on one of these work packages, I will hand it over to Alexei, who will talk a little bit about quantum machine learning specifically. This is really just an example of the work packages that we are overall doing as a program.